Good evening, welcome everybody. Tom Regan's my name. I'm the Vice Chair of the Royal Oak Environmental Advisory Board. And we were approached by Royal Oak resident Tom Allen a few months ago. He said there's this really good speaker from the University of Michigan who would give us a good talk on climate change. So we said, let's get him here. So thank you, Tom Allen, for recommending that. I'd like to introduce Christopher Skinner from the University of Michigan. He's going to tell us if hurricanes are caused by global warming.
Great, thank you. And thank you, Tom, for the invitation again to speak. The last time I gave this talk was in the fall of 2017, and it was really a timely talk to give a presentation called Does Global Warming Cause Hurricanes? Because it was on November 30th, which was the last day of the hurricane season. And it was a very, very active hurricane season in 2017, and in some aspects it was a historical season. So a lot of people were wondering this exact question. And I showed this last time, but I want to bring it up again. If you typed in "does global warming" into Google on November 30th of 2017, the second most common Google response was, "Does global warming cause hurricanes?" If you type in "does global warming" into Google today, this was from this morning, you don't get the same response. You don't get this "does global warming cause hurricanes" suggestion from Google. I'm not entirely sure why you only get 3 suggestions now as opposed to 10 before. But the reason why we're not getting this suggestion anymore is because Google's algorithm, which determines what to put here, its algorithm determines what to put here based on what people have been Googling in the recent weeks to months. So no one's Googling this question anymore. And part of that reason is because this isn't hurricane season. But the other reason for that, and I think this is more broadly the grand challenge of getting people motivated to do something about climate change, is that we tend to forget. We have a recency weighting bias, which is to say that we put a higher value or higher weight on events that just happened in the recent past as opposed to events that happened further back in the past. So when we don't have hurricanes for a while, people tend to forget about this connection between global warming and hurricanes, and we sort of put the whole global warming idea on the back burner until it rears its head again. So this, like I said, is a really big challenge for getting people motivated about climate change, because while we don't see this question anymore, what does carry over, if you can read this here, is does global warming exist? The third most common suggestion, that was the first most common suggestion in November. So that sort of skepticism still exists, unfortunately. So the 2 here, does global warming affect animals, does global warming affect agriculture, and does global warming exist? Those are the 3. The reason why there's this animal question here is because the United Nations just recently released a report that summarized or synthesized the impacts of climate change on ecosystems. So people have been interested in that. So getting back to this larger question, though, does global warming cause hurricanes? So the simple answer to that is definitely no. Global warming does not cause hurricanes. But the question that we want to ask, or the series of questions we want to ask, are slightly more nuanced. Does global warming increase or decrease the number of hurricanes? Does it strengthen or weaken hurricanes? And does it relocate them to other parts of the globe? And definitely feel free to ask me any questions at any point if you need me to clarify. So these are the questions that we are asking in our research right now. And the reason why people have been so interested in this question, particularly in 2017, was because this was the scene on September 6th of last fall. There were 3 hurricanes all threatening land at the same time in the Atlantic Basin. And this was just 1 week after Hurricane Harvey had hit Houston and basically stalled there for 3 days, essentially inundating the city with water. So this is not unprecedented, but it is very rare to have 3 hurricanes at the same exact time in the same basin. And the fact that there were all 3 of them were threatening land was really, really unusual. So let's put this into some perspective. So the Atlantic tropical cyclone season in 2017, this is a map of all the different trajectories that the different tropical cyclones took in the Atlantic. So tropical cyclone is an umbrella term for tropical depressions, tropical storms, and for hurricanes. So if you want to become a hurricane, you first have to go through 2 stages. You have to become a tropical depression first. So that's a fairly weak storm that forms in the tropics, and the winds are generally less than 40 miles per hour. Once you strengthen past 40 miles per hour, you become a tropical storm. Tropical storms are when we start to name those systems. So before Hurricane Harvey was a hurricane, it was Tropical Storm Harvey. So tropical storms have winds between about 40 and 73 miles per hour. Once you strengthen beyond 73 miles per hour, you become a hurricane. And in 2017, there were 18 tropical depressions, 17 of which strengthened into tropical storms, and 10 of those became hurricanes. And what's really sort of the takeaway from the season was that there were 6 major hurricanes. And so when I say major hurricane, I mean a hurricane that was either a category 3, 4, or 5. So this is the scale that we use for hurricanes. It's based on the strength of the winds, and it was developed by these 2 scientists, Safier and Simpson, back in the mid-20th century. So anything above category 3, which is 111 miles per hour, sustained winds and greater, that's a major hurricane. So we had 6 of those in 2017, and 2 of them were category 5 storms. So this is only the 6th time ever in our recorded history, which is more than 100 years, where we've had multiple category 5 storms in the Atlantic. And it's only the 2nd time that 2 of them made landfall. So 2 category 5 storms ran into land while they were category 5 storms. And of those 2, Hurricane Irma was the strongest hurricane ever recorded in the Atlantic Basin. In total, these systems resulted in 464 fatalities and about $320 billion US in damage. So I want to get into sort of why this season was so interesting. Maybe the overall season itself was not a record setter, but the individual storms themselves were record setters. So sort of going through the cast of characters here. Hurricane Harvey was the one that hit Houston. This is the first major hurricane of the season. It was actually the first major hurricane that made landfall in the United States since 2005. So we had gone for more than a decade without experiencing one of these systems. So we were very lucky for a long time. So Hurricane Harvey hit Houston, and it wasn't the winds that were so important with this system. They didn't cause that much damage. What was really important and caused a lot of damage was the rainfall. So the system just stalled. It just sat over Houston for 3 or 4 days straight, didn't move anywhere, and it dumped up to 60 inches of rain on parts of Texas. So just for reference, that's about a whole year's worth of their rain usually. So that was a tremendous amount of rainfall. It's set records for the entire United States. It was the most rainfall ever recorded from one storm system. If you were to take all the water that fell on the state of Texas and Louisiana and Alabama and put it into a cube, the Washington Post made this graphic here. This is downtown Houston for scale. This would have resulted in a cube of 3.1 miles by 3.1 miles by 3.1 miles of water. So that's 33 trillion gallons of water that was moved out of the Gulf of Mexico onto land via rainfall. It's really staggering. And of course, this is made a lot worse because Houston has undergone tremendous urban sprawl over the past 20 years or so. So there was nowhere for that water to go. It couldn't seep into the land, so it just ran off onto the concrete and essentially flooded very large portions of the city. So that was Hurricane Harvey. Hurricane Irma, which I said before was the strongest hurricane ever recorded in the Atlantic, it had sustained winds of 180 miles per hour. And unfortunately, Hurricane Irma hit the island of Barbuda. So this is a satellite image of what Barbuda looked like before the hurricane at the end of August, and this is what it looked like just a few days after the hurricane hit. So this one on the left is a lot more green. This is because all of the vegetation on the trees essentially were ripped off via the wind, or a lot of salt water was picked up by the hurricane and deposited on the leaves, and essentially that desiccated or dried out the leaves, and they all just fell off the tree. So essentially there was no standing vegetation left on this island after the hurricane hit. Just for reference, this is the strongest hurricane that ever hit in the Atlantic Basin. It's not the strongest hurricane ever. The strongest hurricane ever was Hurricane Patricia in 2015, and that one was 215 mile an hour sustained winds, which is the equivalent of an F5 tornado. And that formed in the Pacific Ocean just off the coast of Mexico. But this was the strongest ever in the Atlantic. Hurricane Maria, this is the one that we heard a lot about because of its impacts on Puerto Rico. This is rainfall rates here. This is how much rain fell from Hurricane Maria. As you see, there's a lot of dark purple here. That's about 20 to 28 inches of rainfall. It's a tremendous amount of rain. But really the biggest impact from the system were the winds and the loss of power across the island. So 100% of the island lost power. It took nearly 7 months to return the whole island to power. So as of last week, there was 97% of the island with power. So 3% of the island still doesn't have power. And then they recently just experienced another setback, I think last week. Really devastating impacts for the island of Puerto Rico. And so this was not even a Category 5, this was just a Category 4 when it hit. And the last one I want to talk about is Hurricane Ophelia. This one we didn't hear much about because it wasn't that devastating in terms of its damage, but it's a really interesting system. So this is it right here. This is a visualization from NASA. And it's the easternmost major Atlantic hurricane. So there's never been a hurricane of Category 3 or higher strength this far east in the Atlantic. And it actually went and tracked just to the west of the Sahara. And this is dust coming off the Sahara. It actually picked up a lot of dust and deposited that dust into northern Europe. The other really interesting thing that happened with this system was that, unfortunately, so this white here in Portugal, this is smoke from wildfires. This system went right by Portugal as there was a large wildfire and essentially fanned the fire and spread it a lot further than it otherwise would have gone. This is sort of like the worst nightmare. Strong hurricanes interacting with wildfires. This is not something that we generally see, but 2017 was a very, very anomalous year. So, yeah.
Was there much rain associated with that?
With that one, not so much. Generally, by the time you make it to this portion of the Atlantic, the temperatures in the ocean are much cooler, and so you don't evaporate as much water in general. So it hit England, but England got some rain and some wind, but it was mostly just sort of an interesting case. Okay, so that was sort of the motivation for why we're even thinking about, does global warming cause hurricanes? So in my talk today, I'm going to first give a little bit of a status update on global warming in 2018. What is the evidence for global warming? And then I'm going to talk about extreme weather. So can we actually attribute the changes in extreme weather that we're seeing to global warming? Are humans responsible for things like the hurricanes that we just saw in 2017? And then lastly, I'll talk about some projections of future climate and sort of think about how climate change may impact us here in Michigan, and then give you a little bit of a seasonal forecast as well. So again, what is the evidence for global warming right now? Well, global warming is definitely real, and in 2017 it was the third warmest year on record. So this is a map of the different temperature anomalies. So wherever you see red, it was above average in terms of the annual temperature. And so this is when I say above average, I mean above the mean temperature of the 20th century. So essentially red everywhere. In the United States, the warmest temperatures were in the Southwest. So it's the third warmest. It trails 2016 and 2015 as the two warmest years. So 2016 was the warmest, 2015 was the second warmest. And interestingly, 2015 and 2016 were El Nino years. And so El Nino is a natural fluctuation in the climate system. And generally during an El Nino year, we have warmer temperatures. So that was the reason why these happened to be extra warm. So 2017 was the warmest year ever that was not an El Nino. And so here is that same sort of global temperature anomaly, but plotted over time. So this is the late 1800s all the way through the present day. And so again, the zero line here, this is your average. And so these are the departures from average through time. So the beginning of the century was a much cooler time. As you see, there's a pretty strong increasing trend of temperature warming here over the globe. 2016 is this line right here. 2017 is the one right next to it. 2015 is right there. 2016 was about 1.7 or 1.8 degrees Fahrenheit above average, and so 2017 was about 1.5 or so. If you look at all 17 years that have occurred after the year 2000, all 17 of them rank among the 18th warmest ever on record. The only year that was before 2000 was 1998, and that was a really, really strong El Nino year. So anyone who tells you that global warming has paused is incorrect. It is warming considerably over the past few years. So what about in Michigan? Well, Michigan is following the global trend. So it has been warming across Michigan. So this is the state average, again, starting from about 1900 to the present day. In general, the state of Michigan is warming by about 0.2 degrees Fahrenheit every decade. So it's about 2 degrees warmer on average today than it was about 100 years ago. And so that doesn't mean we can't have cold years, right? So this is 2014 right here. This was a cold year. If you remember the winter of 2014, that was my first winter moving here from California. I was regretting it immediately. It's a very rude introduction to the state. But you can still have cold years, but in general, the trend is much warmer. So that was temperature. As my advisor would always say, if you believe in thermometers, you believe in global warming. If you don't believe in thermometers for some reason, there are other indicators for indicators that the Earth is actually warming. So one of them is by looking at the ice. So we can look at this, for example, in the lake ice in the Great Lakes. So each one of these is a different year, and it shows the maximum ice coverage. So wherever you see white is, it means that portion of the lake is essentially entirely covered in ice at some point during the year. And so wherever you see blue, there's more open water. So here's that plotted on a timeline here, starting from the mid-1970s to the present day. So I didn't draw a trend line on here, but this is definitely going downwards. You can even just compare each one of these dots is a different year. And the years in the 1970s, 1980s, and early 90s all exhibited above average ice coverage. Now we have many more years that are below average here. If you look at the closest lake to us, Lake Erie, this is the lake that generally freezes over pretty much every year, or it used to at least. This is ice coverage here, starting from, the 1970s through the present day. Pretty much every year during the 70s, 80s, and early 90s, you had close to 100% ice coverage in Lake Erie during the winter. If you look at the past 20 years or so, we have many, many more years where ice coverage doesn't even reach 40%. If you're curious what the lakes look like today, this is 2 days ago. Pretty much the lakes are all ice-free except for portions of Lake Superior. So you can go out on the water now. It's not just the Great Lakes, it's also ice that's forming in the oceans. So this is an indicator of melting sea ice in the Arctic. So this, again, is each clip is a different year, and it begins in the late 1970s. And the reason why all of these start in the 70s is because that's when we put the satellites into space that can measure all of these things really accurately. So this red line here is the median value over time. So I think it's the median from, what does that say? 1980 to about 2010, and the white is the ice coverage. So you can see over time, as we get closer to the present day, that ice coverage is shrinking every single year. You can look at this also. This is January here through the winter and spring months. Here's the summer. Sea ice generally reaches its minimum in about September, and then starts to grow back again. So this gray line here is the median value of ice coverage throughout the year. And each one of these colored lines are the past, 7 years or so. And so all of these recent years have fallen below that median value. So 2012 was the lowest sea ice coverage extent that we've ever had. 2018, it's kind of hard to see. It's this orange one right here. It's actually tracking lower than all the other years during the past couple of months. So it's either the lowest ice coverage right now or the second lowest ever recorded for this time of year. So it'll be interesting to see how this looks come September when we're at the minimum here. Projections of climate change going forward this century pretty much all point towards an ice-free Arctic during the summer. So there'll be ice in the winter still, but during the summer, this will go to zero. So there'll be no ice there.
How many years are you predicting?
That should, according to most climate models that project sea ice loss, that should occur in the late portion of the century, so 2070 to 2080 or so. That's a bad thing because when there's no ice there, the solar heating during the summer warms up the ocean, and it becomes harder to form ice in the winter, and so there's a very strong positive feedback there. So ice is melting in the Great Lakes, it's melting in the Arctic, but those two things don't actually increase sea level because that water's basically already that ice is already in the water. The ice that's on the land, though, that is contributing to sea level rise. So this is a picture of Greenland, and what I'm showing here is the reflectivity of Greenland. So wherever you see blue means that Greenland is becoming less reflective. And the reason for that is because all the snow that falls during the winter melts much quicker now, and it exposes much older ice. That ice has a lot of dirt and dust sort of stuck into it. And so that means that the surface of Greenland is much darker than it used to be when there was much more snow cover on it. Again, that's a problem because when the sun hits Greenland now, it doesn't reflect away. It's absorbed by the much darker surface, and that accelerates melting in Greenland. So this is happening. Greenland is melting at a very rapid rate right now. Interestingly, this past year, there was a wildfire. So on the edges of Greenland, there actually isn't ice over the whole thing. And so somebody, this is human caused, I don't know what they were doing here, but they caused a fire. And similar to what I'm showing here, the smoke from that fire then spread out over the ice sheet itself, and the ash fell down on the ice sheet and darkened the surface, and then that led to much more solar energy being absorbed on Greenland, and that accelerated the melt. Yeah, this is not a good thing to see, and this is contributing to sea level rise. And so this is a map or a plot of sea level rise from the early 1990s to the present day. Again, this is something that we can measure from satellites. So that's why it begins in the early 90s when we started measuring this. And over this time, the sea level has been rising by about 3.4 millimeters every single year. So that's about 80 millimeters since the early 90s. If all of Greenland were to melt, that's not something that's supposed to happen anytime soon, or potentially ever. But if it were, sea level would rise by 20 feet. If all of Antarctica were to melt, I don't actually know the number, but it would be something considerably higher than 20 feet. So estimates for sea level rise this century range from anywhere from about 1.5 feet to 3.5 feet, depending on how much CO2 we emit as humans. So speaking of that CO2, this is another indicator of global warming. We know that rising CO2 in the atmosphere warms the temperatures. This is the greenhouse effect. We've known about this since the 1800s. So this is a plot that shows the amount of CO2 in the atmosphere. So this is measured directly from the atmosphere. They scoop up air and measure the concentration. And the concentration is in something called parts per million. And so in the late 1950s, when we started measuring this, CO2 concentrations were about 310 parts per million or so. Now CO2 concentrations are about 410 parts per million. So this is a very large increase in CO2. As of 2 days ago, CO2 is about 412 parts per million in the atmosphere. This is probably the highest it's going to get this year. So April is basically when you peak in terms of CO2 concentrations. And so if you actually zoom in on a 2-year time slice and we blow it up, this is what the CO2 looks like as you go through the course of the year. So it actually dips up and down. And so during the summer months, CO2 in the atmosphere actually goes down. So this is July, August here, September. That's because plants are taking CO2 out of the atmosphere for photosynthesis. When the plants die in the fall and the winter, that CO2 is released back into the atmosphere, and it peaks right around this time when plants have been dead for the longest period of time. So in a few weeks, plants will come out, take in more CO2, and this will start to drop again. But the overall trend is very clearly upward. And so what does this look like compared to the distant past? Well, this is where we are today. This is where we were in 2016, about 403 parts per million on average. This is what it looks like for the past 800,000 years. So this comes from ice cores from Antarctica or from Greenland. So the CO2 is trapped in air inside the ice, and then we can drill into the ice sheet and pull out that core and analyze the air that's trapped in that ice. So the longest cores go back about 800,000 years. And so we have not even come close to 400 parts per million over that time. There's some other evidence from different paleoclimate indicators that we haven't exceeded 400 parts per million in close to 10 million years. So this is quite unprecedented for a very long time. So who's to blame for the CO2? Well, it's not surprising that it's us, it's the United States and Europe for the recent past, so beginning from the Industrial Revolution. So this actually starts in 1960 and goes to the present day. So we are this light blue color here, the United States. The dark blue is the European Union, which includes, I think it includes England here, and or United Kingdom, England, yeah, Britain. And this gray one here is the rest of the world combined. Every single other country other than the European Union, the United States, India, and China. So the United States and Europe have been largely responsible for this. But recently, China has overtaken the United States and the European Union. So China is now the #1 emitter of CO2 in the world. But if you break this down into the amount of carbon that we emit per person, the United States is still very clearly the leader here, just above Canada. So China is more towards the middle of the pack. So the past 3 years, so 2014, 15, 16, CO2 emissions actually stalled. They did not increase, and people were excited that perhaps we had peaked and we weren't going to emit any more CO2. Well, 2017 saw a 2% rise in CO2 emissions. So people who have been saying that CO2 is going to peak right now are probably a little bit early in that call. This rise here was largely because China emitted quite a bit more CO2 this past year than they had in the previous years. And so this results in disastrous climate and weather events. And so this is sort of a transition to the second part of the talk. These are billion-dollar weather and climate disasters from 2017. So there were 16 individual weather events that caused at least $1 billion in this country just last year. So there were the hurricanes, the wildfires in California. There's severe weather generally in the center of the United States. So Michigan was pretty much spared. The Northeast was pretty much spared of these events this past year. But in total, including the United States and the rest of the world, there was about $330 billion in damage caused by weather events this year. This is an image that I just like to show because it sort of shows you how common these crazy weather events have become and how comfortable we've sort of become with them. This is a group of people that are finishing up their game of golf while this wildfire is burning in the background. This is a real photo. You can't really tell, this is a little bit further back, so I guess they were somewhat safe, but I think it sort of symbolizes or epitomizes everything that I'm saying here. These have become the norm almost, and so we can finish our game of golf and not even really care about this going on in the background. This is from Oregon, I think. Okay, so observed changes in extreme weather. So can we attribute these changes that we're seeing to human-caused climate change? Are we responsible for the hurricanes that we saw? So there's two ways in which we can sort of ask this question or answer this question. And these are pretty much the two approaches that everyone is taking in our field right now. They're very, very active areas of research. The first is an ingredients-based approach. So rather than say, was this hurricane caused by climate change? We can say, well, did the ingredients that contributed to that hurricane, did those change because of human emissions? So it's more of an ingredients-based approach or an environmental conditions-based approach. And I'll go through an example with hurricanes in a second. The other way of doing this is much harder. It's called probabilistic extreme event attribution. It requires really powerful computer simulations and a lot of statistics, but I'll very quickly talk about that as well if we're interested. But looking at this ingredients-based approach. So what do I mean by that? Well, what I mean is take the event that you care about, so in this case, a hurricane. The first thing you need to know is what makes a hurricane in the first place. So there's really 4 ingredients that make a hurricane. The first is that you need an initial cluster of thunderstorms. The second is you need warm water, warm ocean temperatures. You need moist air or high humidity, and you need really light winds in terms of the shear. So wind shear is the change in the speed or direction of wind as you go up in the atmosphere. So if there's really light winds at the surface but really strong winds higher up in the atmosphere, that's high shear. So that would destroy a hurricane. So you need light winds or low shear. So the question that we ask is global warming influencing these ingredients? And that will give us some indication of whether or not hurricanes are becoming more likely or more intense because of our activities. So let's go through each one of these ingredients. So the first one is an initial cluster of thunderstorms. This one is probably the least researched to this point. I've spent quite a bit of time thinking about this question. And I don't want to bore you with my research, but I want to bring up a point that I think is interesting that a lot of people don't know. So pretty much all hurricanes in the Atlantic, 70% of them at least, actually start as a thunderstorm or a cluster of thunderstorms over Africa, so just south of the Sahara Desert. And they move off the coast, and then they undergo what's called tropical cyclogenesis and become hurricanes in the Atlantic Basin. So the first ingredient you need is this cluster of thunderstorms moving off of Africa. So is there any evidence that these thunderstorms have become more likely, or have these thunderstorms become stronger? Well, the answer to that is unclear. We don't know. So is there a human fingerprint for this? We don't know. They have not become weaker and they haven't become less frequent, but they haven't really become any stronger or more frequent. So this is one that we don't really have a good answer for. So it's a good research question for us to look at in the future. Well, so this one's unclear, so we can't really say anything about that ingredient. But the other three ingredients, we can start to say something. So warm water. This one's pretty obvious. As the temperatures have been increasing, the ocean temperatures have also been increasing. So this is the map of the change in sea surface temperature over the 21st century, or over the 20th century, and including the 21st century, the first 15 years. Wherever you see red, the ocean temperatures have been warming. So these are warmed by anywhere between 1 and about 2.5 degrees Fahrenheit. And so that's important because a hurricane, as it moves over the ocean, it needs really, really warm water to support itself. Temperatures need to be about 80 degrees Fahrenheit for a hurricane to form. So any warming of the ocean water increases the chances that that water is going to be more than 80 degrees Fahrenheit. And so thinking about what went on in August and September of 2017 when we had all of those hurricanes, this is a movie here. Each one of these clips is, I think, 2 or 3 days in the future, or they're separated by 2 or 3 days. And it's the anomaly in temperature, or the departure from average. Wherever you see yellow or orange, that's warmer than usual temperatures. So if we start in August, which is now, it's all much, much warmer. It's all yellow. And then you start to see some blue sneaking in here. And that's really interesting. So the point is that in August, it was much, much warmer than usual, so that supported these hurricanes. The blue that you're seeing here is actually when a hurricane moves over the water, it churns up the water and actually brings cold water up to the surface. So that you can actually see where the hurricanes are moving through in August and September. It's really cool. This is the reason why you generally don't see a lot of hurricanes clustered right next to each other. When one hurricane moves through, it churns up a lot of cold water, and then the next hurricane that tries to move over that water, the water's not warm enough to support the hurricane, and so it doesn't actually form. So this past year, having 3 hurricanes all at the same time was really, really unique. The water was so warm that it was able to support those hurricanes. So is warmer water making hurricanes stronger and more frequent? Absolutely yes. And this is the result of human activities. There's no doubt about it. So one of the ingredients is definitely increasing. The next ingredient would be moist air, or high humidity in the atmosphere. And so this is a plot of what happens to humidity. This is essentially humidity. It's the saturated vapor pressure versus temperature. And so as you increase the temperature, there's this exponential relationship here that basically says you can hold 7% more water in the atmosphere for every 1 degree Celsius warming that you have. So as you start to get warmer and warmer and warmer, you can hold more and more water in the atmosphere. And this is something that we're seeing. So these lines here, again, these are from satellites, so they begin in the 70s and they go to the present day. So orange is land, blue is over the water. This is how the humidity in the atmosphere is changing over time. And again, it's increasing because we're increasing the temperature of the atmosphere. So this is important because when you have more water in the atmosphere, that serves as fuel to the hurricane in the form of latent heat. So the water vapor condenses, that releases a lot of heat, and that sort of powers the storm system. So is moisture in the atmosphere increasing? Definitely yes. So this is, again, a human-caused change that we're seeing, and this is definitely contributing to stronger hurricanes. So that's 2 definite yeses to this sort of ingredients approach. The last one is light winds or low shear. This one's a little bit harder again. So like I said, if you have really strong shear, which is like sort of this represented by these arrows here, it sort of tips the hurricane over and sort of rips it apart. And so it can't really get that strong. If you have really light shear, you have much stronger hurricanes. So in El Nino years, you tend to have really high shear. You tend to see lower hurricanes. This is a really useful tool. If you know it's going to be an El Nino year, you can basically predict that there are going to be fewer hurricanes. During a La Nina year, which 2017 was, there was a much lower shear, and that was one of the reasons why we saw much more hurricanes in 2017. So we had warm water, we had more moisture in the atmosphere, and it was a La Nina year, so there was low shear. So all of those 3 ingredients together made 2017 a very active hurricane season. But this is not something that we can attribute to human activity. This is a natural variability here. There's no real evidence that people have decreased the amount of shear in the winds in the atmosphere. So this one, again, is unclear. Again, we haven't increased the amount of shear, we haven't probably decreased it either. So 2 out of the 4 ingredients are definite yeses. So this is the approach that you can take to sort of ask these questions. Have we increased hurricane intensity? When you take this ingredients-based approach, the answer is yes, because 2 of the ingredients we have definitely increased. So thinking about that in the context of 2017, much warmer temperatures increased the storm system intensity and the rainfall. There was low wind shear, but this again was not because of humans. This is because it was a La Nina year. And then really what really matters is the impacts. And these impacts are made worse, yes, because the storms were stronger themselves, but also because we have exposed a lot more infrastructure to those systems. We've exposed more humans to those systems as we settled along the coast. So this is sort of a really important one that we need to remember as well. So 2017 was definitely an active season, in part because of human activities, but a lot of it was also just natural variability and because we sort of exposed our assets to those systems. So I just want to return to this graph here because I think this is one of the most important things that I could talk about here, this relationship between temperature and the amount of water in the atmosphere. So this is called the Clausius-Clapeyron relationship. And like I said, there's a 7% increase in water vapor for every 1 degree Celsius that you increase the temperature. And so humidity has been increasing. This is the reason why we're seeing heavier rainfall events across the world. And so this is from the United States. This is the trend in heavy downpours. So days in which you have more than 1 inch of rainfall. So these are on the increase across the United States. So this is largely an artifact of, or a response to the fact that the atmosphere is just holding more water. So when it rains, there's more water to condense and fall out. This is actually fairly straightforward thermodynamics. So what does that look like across the country? Well, in the Midwest and the Northeast, we're actually seeing the largest increase in the number of downpours that we experience each year. So there's been about a 42% increase over the Midwest in downpours over the past 50 years. A little bit less so in the Southwest, but the Northeast and the Midwest are increasing, and this is the number of downpours in the state of Michigan. And so again, this is the number of days each year where you have a downpour. So again, how far does this go back? To the 50s. So these actually come from observational stations throughout the state. So you were averaging about 8 events per year back in the 50s, and now we're looking at something closer to 10 to maybe 11 events per year. And so this is projected to increase, and I'll talk about that a little bit in the third part of the talk. And so I mentioned this other approach, this probabilistic extreme event attribution approach. This is a little bit more complicated, and I don't want to get too far into the details here, but what this requires, like I said, is intense climate model simulations. And so basically, you take a climate model, which is just like a weather model, but you run it for a longer period of time, and you run that model with high CO2, the CO2 that we experience today, and then you run the same model. Everything is the same except you don't allow the CO2 increase. So you run a situation where the CO2 is like 300 parts per million or something, and then we run it with 400 parts per million in a different simulation. And you compare the two. And so to do that, you need to use these really, really impressive climate models. And like I said, these are like weather models, but they're much more intensive. And you run them for hundreds of years in those two scenarios, one with low CO2 and one with high CO2. And then you just compare the climates. You do this maybe thousands of times, and then you employ some really impressive statistics, and you determine whether or not that specific event became more likely in the model simulation that had high CO2 compared to the model simulation that had low CO2. So this sort of is contingent upon the fact that the model is able to simulate the event that you care about. So climate models generally are not that good at simulating hurricanes, so it's hard to do this approach when you're thinking about something like hurricanes. They are good at other things, though. So this is a map of this is a model simulation, climate model simulation, and this is actually from a satellite. So this one is slowed down, but yeah, so these are running at different speeds, but what you see is that the model does a really good job at simulating a lot of the features that we see in the real world. So these are really impressive machines that we can ask certain questions of. We just can't ask all questions of them. And so what can we ask? Well, we can ask things like, are extreme heat events becoming more likely? Are extreme cold events becoming more likely? Droughts, extreme rainfall, that also sort of falls on this schematic of things that we understand fairly we understand them quite well, and the models can simulate them. Things like severe convective storms, wildfires, tropical cyclones. These are things that we really can't simulate that well, so we can't use this approach so much. So that's why we use the ingredients-based approach to ask questions like, are hurricanes increasing? But we can use models to study things like extreme cold, extreme heat, droughts, and stuff in events like that. And so this has been used, this approach, to detect a human fingerprint on things like the European heat wave in 2003, which caused thousands of deaths. The 2010 to 2015 California drought, that was absolutely in part driven by human emissions of CO2. And the flooding event in Louisiana in 2016, this was another one that was definitely attributed to human activities. We've also been able to use this approach to show that things like the 2013 Colorado flood were probably not driven by human activities. So this is a really interesting and useful technique, but it is limited in what you can ask as of right now. Maybe in about 10 to 15 years, when models get better at simulating these types of events, we can use this approach for those as well. But right now, we have to stick to the ingredients-based approach for those types of systems. Okay, so I just want to end with some projections of the future climate and focus a little bit on what's going to happen in Michigan. People ask me what's going to happen in the future, and the thing I always tell them is that there's a lot of uncertainty, but the biggest uncertainty is what people do. So there's uncertainty what might happen to clouds, there's uncertainty what might happen to different physical processes, but humans are without a doubt the number one source of uncertainty. So economists and scientists get together and they come up with these different scenarios that we could take. And these scenarios are based around our choices, largely our choices about what we do for energy in the future. So there are different scenarios. So this red scenario here, this is time on the x-axis, and this is, for example, CO2 in the atmosphere on the y-axis. So this red scenario here, this is what's known as a business as usual scenario. If we sort of explode in population and we are committed to a carbon-based economy where we do not scale up renewables, we would take this line here. So CO2 by the end of this century, if we take that trajectory, would be about 900 parts per million in the atmosphere. So again, today it's about 410. This is more than doubling. There are other trajectories we could take that have lower CO2 emissions associated with them. I'm not very optimistic about these two. These are essentially not possible. This orange one is definitely possible, but we're probably going to, this is just my opinion, we're probably going to follow something in between these two right here. As of right now, we are absolutely following this red line. We are closer to this red line than any of the other scenarios. What does that mean for temperature? Well, if we follow that red line, which is the red line here, by the end of this century, the global average temperature will have increased on average by about 7 degrees, 8 degrees Celsius. That's about 14 degrees Fahrenheit across the globe. If we take something like this orange line, the projections are more along the lines of about 7 to 8 degrees Fahrenheit. Okay. So this is a large source of uncertainty. What do we do with carbon? So what does that look like in terms of the United States? Well, so anything that's on the left side here is if we take that orange trajectory, the sort of middle of the road scenario that we could take if we take some steps to reduce our carbon emissions. And everything on the right side I'm going to show is this red trajectory here. So this is temperature change averaged over the year for the United States, Canada, and Mexico. So obviously the colors are lighter on the left side. So this is the middle of the 21st century in the top, so about 2040 to 2070, I think. And the bottom is the end of the century, so about 2080 to 2100. So these are changes in temperature in degrees Fahrenheit. So if we were to take the high scenario, by the middle of this century, temperatures are anywhere from about 4 to 6 degrees warmer on average in Michigan and across the United States. If we were to continue along that trajectory until the end of the century, we're talking about, again, temperatures 8 to 10 to potentially 12 degrees Fahrenheit warmer in Michigan. Much warmer in the higher latitudes where you have something that's known as Arctic amplification. So the high latitudes warm a lot more than the rest of the globe. If we take that lower scenario, well, it's much better. We're talking about somewhere between 2 and 4 degrees by the middle of the century and something maybe as high as 6 degrees by the end of the century. So this is averaged over the year, by the way, so there's going to be extreme events that are a lot warmer than this. So what does that look like in terms of the projected change in the number of days that we exceed 90 degrees Fahrenheit? So in Michigan, we're talking about somewhere between about 20 and 30, maybe 40 more days every single year where the temperature exceeds 90 degrees Fahrenheit. So those are the days that are really uncomfortable. This is, again, if we take that red scenario to the end of the century. Actually, this is the middle of the century, sorry. And this is the number of days below 32, so maybe something that's good, but it depends who you ask. So fewer days where it falls below freezing, maybe 20 to 30 less days per year. So like I said, when temperature increases, the moisture in the atmosphere also increases. And when those two things combine together, that's when we have a really dangerous day. It's known as a heat index. It's when you combine the humidity with the temperature. And so this is a projection for the middle of the century for Detroit, Michigan. 23 more days per year where you have a heat index above 105. That's essentially the point where it's really hard to sweat. You don't want to go outside, you need air conditioning. It's a very dangerous situation for a lot of people. So this, again, middle of the century, if we take the trajectory that we are currently on, this is what it looks like for Detroit, Michigan, or this general area. You can't project a particular city. This is sort of emblematic of the entire Midwest. So there's a couple more. This one is the projected change in heavy precipitation events. So it's a little bit hard to see, but essentially, again, mid-century here, late century on the right. Because we have more moisture in the atmosphere, we're going to see increases of 10 to 15% in the number of really, really 20 years. Like these are events that happen with a 5% chance. These are 10 to 15% increase in those types of rainfall events. Much, much higher when you take, again, this high emission scenario into the late century. So more than 20% increase in these really, really heavy rainfall events. So much hotter, much more humid. And again, when it rains, it's going to rain a lot heavier. And the Midwest is really sort of the hot spot in the United States for these types of events. So I just wanted to point you to a couple of resources where I got a lot of these graphs. If you're interested, Climate Central makes a large number of really nice graphics that I showed. Climate.gov, National Center for Environmental Information, if you want to look at individual sort of state level climate data. And if you're on Twitter, #StateOfClimate gives you the update, so what's going on. So the month of March, for example, was pretty cool here, but globally it was still the 5th warmest March ever recorded. So they tell you sort of facts like that, so you can get some idea. So thinking about what's going to happen this year, if we're interested in what's going to happen for hurricanes, well, one of the most useful things that we can know is that this year is not going to be an El Nino year. So if it was an El Nino, if you remember, there's a lot of wind shear in that. So this is going to be an average wind shear year, which means that we should see at least average numbers of hurricanes in the Atlantic Basin. We know that the ocean temperatures are going to be slightly above average. So 2018 looks like there's going to be slightly above average numbers of named storms. So these are tropical storms, and slightly above average number of hurricanes as well. And this is actually predicting slightly more strong, really, really strong Category 3 hurricanes or higher as well. As a disclaimer, this group here, this is Colorado State University, is the one that makes this prediction. Last year they were way, way off. So it happens. Last year was a very anomalous year. No one saw that coming, actually. Last year was supposed to be sort of an El Nino year, but it actually transitioned to a La Nina year really quickly. And that was one of the reasons why we saw that miscalculation. But we have very good confidence that this is not going to be an El Nino year, so there should be at least average hurricane potential in the Atlantic. Yeah?
Do tornadoes occur similarly to hurricanes with the warmth and the heat index up?
Yeah, so if we looked at this graph here, so tornadoes would follow, they wouldn't even be this category, they would be basically here. So we have essentially no ability to simulate those types of events, unfortunately. So we can't use that type of model-based sort of fingerprinting. But in general, if we take the ingredients-based approach, the ingredients that support tornadoes are definitely becoming more likely. Tornadoes are interesting. They actually like high shear. So the more shear you have, the more tornadoes you generally have. It's very hard to do seasonal projections of things like tornado activity. but there should be more tornadoes as we go into a warmer world because there's essentially more energy in the atmosphere. But that's something that we can't really simulate at all right now. Okay, so average hurricane season. The last thing I want to show is what about us over the next few weeks. So last year I gave this talk and I told everyone that there was going to be a polar vortex, and it actually did happen right after I told you it was going to happen, so I was really excited about that. So things aren't as interesting right now, so I don't have any really interesting forecasts here. But so this is what it looks like for next week. It's going to be considerably warmer than usual over Michigan, definitely. Very, very high confidence that next week is going to be very warm. The following week, however, is actually going to drop down for some very seasonally cool weather. These are generally it's hard to predict out 2 weeks in advance, but all the models right now are pointing to this weather pattern here. So blue is cool, red is warm, and this is Michigan here. So next week, really, really nice and summery. The week after, return to sort of weather more like today. Otherwise, there's nothing too interesting going on. But if you want to have really good seasonal projections, what's going to happen over the next couple of weeks, this is the guy that you want to follow, Judah Cohen. And this is his Twitter handle if you're on Twitter. But he does the most accurate seasonal predictions. He was the one that knew that we were going to have that polar vortex event at the end of December, early January. So with that, I'll take any questions if you have them. Thanks.
I was just visiting Boston, and most of the valuable land there is built in the ocean, so when the oceans rise 3 feet, it's going to be underwater.
Yeah.
But there doesn't seem to be any planning for that. Are people just like in denial at this point? Or?
A lot of people definitely are. I think city planners are waking up to that reality, and they are making some plans. I don't know specifically what Boston is doing. I'm moving to Boston in a couple of months, so
Okay.
I should hopefully find that out. But there is some preparation going on. Mostly it's an adaptation type of approach that we're taking right now, which is necessary, but that's really not the approach we should be taking. We should be taking the action of, just stop emitting CO2 and introduce renewables. But there is some adaptation going on. I'm not entirely sure what Boston is doing. But yeah, if you look at these maps that are produced for what portions of the country are going to be inundated with water as the sea level rises by 3 feet, there are huge portions of Florida, all up and down the East Coast and the West Coast. So, yeah, it's not good.
I keep seeing this note coming in, no firm evidence that shows that this is human effect. What do you need?
What do you need to convince the people that this is human caused?
Well, but statistically, we're well into global warming and it's human activity.
Yeah, there's no doubt.
Why do we keep getting that note? Well, we're not sure. We're not sure.
Yeah.
99% is pretty damn good correlation with the atmospheric carbon dioxide.
Right. Yeah, no, it's a very... It's been going on for a long time. It's the same tactics that were used with the tobacco industry, for example. This is Exxon, this is Shell, this is in a lot of energy industries that are, or in the auto industry as well, that don't want to see regulations, so they dispel this notion of doubt across the country. And they latch on to things like, we don't know what's happening to tornadoes, for example, so we can't say anything about climate change. They'll latch on to one little piece, whereas they're just totally disregarding the rest of the evidence. So what we do about that, I'm not sure. Talks like this, try to tell people the facts, it doesn't seem to be working. So yeah, it's a shame.
I'm just curious, what is your take on the efforts of the current administration to dismantle a lot of the activity that has contributed to this knowledge base?
Yeah.
Not good.
No, yeah, it's definitely not good. I think the EPA is the most salient example of that. They're essentially dismantling a lot of the Obama-era regulations, for example, with gas mileage. Yeah, it's definitely not good. People always ask me, similar to that, how has this impacted the research that we do? Has there been a cut in science funding? The answer is really surprising. It's no. Science funding has gone up since President Trump took office. which is very surprising. And that's because Congress is actually, and the Senate has pushed really hard to continue to fund science, despite what President Trump and his administration wants to do. So they had originally planned, they put their proposal through, which was something like earth sciences were going to be slashed by, I think, 11 to 15%, the funding for that, and then we've actually seen an increase. So it's actually been not so bad so far. But in terms of things like the regulations through the EPA, that's really not good. Yep. But that doesn't impact me particularly.
Are there any other countries that contribute, let's say, more than the United States has contributed to this base of knowledge?
In terms of science funding?
In terms of research activity, the kind of modeling that is necessary to...
Yeah, a lot of countries in Europe are doing a really good job of that. If you remember, I think Macron had said something like, any scientists in the United States who feel like their funding is going to get cut, come to France and we will fund you. I don't know anyone who did that, but they are continuing to, they're still in the Paris Agreement, for example, where the United States has threatened to pull, or is going to pull out. And so they're continuing to put money towards those efforts, whereas we're not. But yeah, I would say Europe is the number one.
We recently lost a giant in the area of what's coming up when Stephen Hawking died. And he was one of the leading people, and he was from the UK. But anyway, his rather disturbing forecast is by 200 years from now, this planet will be unlivable. And that's pretty damn dramatic.
Yeah, it depends
It's one
again
of the best.
what we do in terms of our energy choices. If we continue along that same red line, which
Yep.
for another 100 years past this
Another
one,
hockey stick going up.
yeah, that's essentially an unlivable planet for sure. I'm less pessimistic that I don't think we're ever going to get there. But beyond humans, like so, animals and plants can adapt to the changes that we're seeing that they're going. So this is the Earth is warming at a rate that's faster than anything we've seen in millions of years. And so, even though we may be able to adapt, the rest of the world is not in terms of animals and plants. So yeah.
Things that I've read that I don't seem to see enough of a push about in the general media are how the geopolitical, how like the droughts in northern Africa are actually responsible for a lot of the immigration and a lot of the pushing of people into Europe because they can't farm anymore and they're
Right.
looking for other ways to live.
Right.
And it just seems like, that's such an obvious dynamic.
Yeah.
You don't see a lot about it, or I haven't seen a lot about it in
Yeah, it's true. I
the
mean,
New York Times.
yeah, no, I mean, and there's some evidence that the whole Syrian conflict was at least in
Yeah.
part driven by lack of water. And yeah, there's a tremendous potential for a lot of political instability and climate refugees, essentially, from climate change. That, yeah, you're right, it doesn't get enough attention, for sure. It is hard to pinpoint exactly what the climate contribution was to any conflict, because there's so many factors.
Ingredient model.
Yeah, no, exactly. And so you can say that this probably increased it by X% or whatever. Yes, definitely.
Can you help me understand why the Arctic is warming so much faster than the rest of the planet?
Yeah. So it's called Arctic amplification, and so part of it is, I touched on it a little bit when you, for example, melt the snow or the ice, that exposes the surface underneath, whether that's water, whether that's land. So when you have ice or snow on top of that, it's a very reflective surface. And so a lot of the solar energy that hits that surface is reflected back to space. It keeps temperatures really cool. When you get rid of that reflective surface, that energy is just absorbed right at that local scale, and it goes into warming that area. So it's because right now they're covered in ice and snow primarily. And you get rid of that ice and snow.
Albedo.
Yeah, exactly. The albedo. And that accelerates, that warms up the air, that melts the snow next to it, and continues on. Yeah.
So do you have suggestions on what we can do to, our own way of doing things to, kind of slow this process down?
Yeah, there are a lot of really good books on that for sure. There's one recently that came out, 100 Things That You Can Do Personally to tackle this. At this point, there's only so much that the individual can do. That sounds sort of depressing, but essentially we need government and big industry to start making these steps, and so you can sort of get in contact with your local congressman, congresswoman, and say something there. But otherwise, it's pretty tough. When they say change your light bulbs or something like that, yeah, that definitely helps. You should be doing it, but it's not at the scale that we need right now. So voting, that's really all you can do.
I think all of us would like to know how to speak to friends and relatives who think this is just all made up.
Yeah, that's hard. The advice that I've been told is to try to connect with those people on something that they care about. So bring it to an issue that they're interested in, if it's local weather or something like that. Or
And when you get to the point of trying to see something differently, they'll turn off.
yeah,
Don't go that far.
right. That's really hard.
They're not here.
But this is part of the problem. We talk to each other all the time, and we're a self-selecting group of people, right? So yeah, it's tough.
I'm going to add a couple of comments, and if I'm stepping on anybody's toes, let me know. I've been concerned about the same thing, and a lot of the information I've had is, again, connect about what people care about. So, for example, I was talking to a staffer in Washington, D.C., and they knew this and they knew that, but when I mentioned dogs are getting more ticks, perked up. Oh yeah, my dog, and now we have to go to the vet more often, and we have to get this and that. Some things that I've been trained to look at are costs to the military. If people are concerned about our military security, there are plenty of sources for that kind of information. Kids, of course, a lot of people are concerned about their kids. There's a whole movement of people who are looking at sports. So, for example, Michigan has suffered a lot this year because we have such small snow cover. All the tourism related to snowmobiles and dog sledding and ice fishing and ice climbing, and all those things are down. So, and another option, if any of you are interested, I work with Citizens Climate Lobby, and there'll be 1,300 of us in Washington, D.C. in June. We're meeting with all the members of Congress.
Good for you.
If you want to fill in a little letter over there of, I'm worried about climate for this, and I'd like you to do something or do something specific, we will take your letters to your member of Congress and to both Senators Stabenow and Peters.
Right?
Thank you.
Work with the children.
Yeah,
They change, that they, if they start thinking about it at an early age.
right. Yeah, it needs to be part of the curriculum in school from an early age. Yeah.
I worked with it a long time ago.
Yeah.
In 2014, we had a devastating 5 inches of rain in a very short period of time, which caused tremendous flooding in this area. A number of cities, not this one, are putting their heads in the sand. They believe it's a 1 in 500 storm, 1 in 100 storm, which we know are percentages, not years. Do you feel that this is something that is going to be continuously happening? Does the research show this? I'm very concerned because I see people who are rebuilding their basements, doing all of that, not concerned about finding a way to infiltrate their land, the water into their land through plants and other things and non-porous surfaces. So I'm concerned, and I wondered if you have an opinion on preventing more, an increase.
Yeah, the science is it's we're very confident that there's going to be an increase in those types of events moving forward. There's no doubt. It's already happening. There's a trend in those types of events right now. The Midwest is one of the hotspots for that moving forward. So it's absolutely going to happen. And yeah, you're right. People seem to ignore that. They just want to build again, to make the same mistakes over and over again. People are taking these things into consideration when they're building things like bridges, for example. This is a pretty important, a lot of engineering that takes this climate change aspect into consideration when they're making these choices. I think the last thing I saw, though, was that the Trump administration had removed that provision from one of his big infrastructure bills, actually. So they're making the same mistake at that scale that individual people are making. Yeah, no, the science is totally settled that rainfall events are going to increase in intensity and in frequency. And it's that very simple thermodynamic argument that there's more water in the atmosphere when temperatures are warmer. So, yeah.
So I recently graduated from Michigan, and one of the classes I took there talked about how we were supposed to shift away from using language surrounding global warming to climate change.
Mm-hmm.
And I was curious because your presentation was so forward with addressing this as global warming.
Mm-hmm.
And do you find that you ever have to kind of tune your language based on your audience, or what are your thoughts on that?
Yeah, definitely. Tom suggested the title was "Does Global Warming Cause Hurricanes?" So I'm just going to run with global warming for sure in this talk. But I'm totally fine with calling it global warming because that is what it is. The world is warming. So, and that warming then causes different climate changes. So depending where you are, that could potentially mean colder temperatures very regionally, but again, the globe is definitely warming. But it does depend who you're talking to, absolutely.
So then I guess if the research is all there and it's pretty clear and evident, then why is there this need to have this hidden language to suppress the fact that it's global warming and that it has to be now called climate change and everything like that?
Because when people start to say that increasing CO2, which warms the Earth on a whole, can also cause things like extreme cold temperatures in the Midwest. It's confusing, I think, in part for a lot of people to sort of have those two ideas floating around at the same time, that the Earth is warming, but this global warming actually causes extreme cold events. That's one example. So calling it climate change certainly has some advantages in that sense, keeping everything sort of clear.
It's been a really convenient argument for the naysayers. They go, oh, well, it got cold, so there's
Right.
no global warming.
Right.
So I think that was a big driver behind the change in the language.
Yeah, no, and it definitely makes sense.
People
But-
also argue that these changes have been going on
Right.
millions of years, but that one diagram you showed, that's the first time the ice,
Oh yeah,
Yeah,
I have this
the
other
ice
one
wave
too.
bumps.
That's
that was mind blowing.
so this is temperature. So CO2 hasn't been as high as it has in at least 800,000 years, there's no doubt about it. This is a reconstruction of what temperatures looked like for at least the past 12,000 years. So it actually was quite a bit warmer, 8,000 years ago or so. This is because changes in Earth's orbit actually meant that we were directed at the sun while we were closer to the sun. So it was driven by being closer to the sun. But we're essentially warmer than that now, and we're at the point in our orbit where we're actually furthest away from the sun when we're pointed towards the sun. So it's sort of, we've already basically overcome the changes in orbital cycles just because of the increase in CO2. So yeah, no, if you start to look through the paleoclimate record, people would say things like, oh, it's been warm in the past, and CO2 lags temperature, and all these things, these arguments, but they're all old and they have been debunked. So yeah, I mean, I think the graph with the CO2 is very clear, and that's settled. The ice core records, the measurements of CO2 in those records is very accurate. So. Okay.
Well, let's give our speaker.
Thank you, Dr. Skinner. And again, my name is Tom Regan. I'm the Vice Chair of the Royal Oak Environmental Advisory Board. And there's two ways you can get involved if you're interested in getting involved. Mary, come on up here. First, if you'd like to be a member of the Royal Oak Environmental Advisory Board, we're actually full up right now because a lot of people in Royal Oak are interested in saving the environment. But we've just started a new associate member thing. So if you're interested in being an associate member, which means you're not an official member, appointed by the city commission, but you can still participate in everything we do. We're a bit of a different when it comes to the city board. We don't just sit at meetings and consider things, you know, we're actually out in the community doing stuff. So if you're interested in being an associate member, just give me a call. My phone number is 248-291-9054. And then also here tonight, we've got Mary Dunn. She's Royal Oaks representative for the Citizens Climate Lobby. And Mary, could you step up and just give your contact information if they're interested in contacting you?
Do you want phone number or email address?
Anything for the camera, yes, phone number.
Okay. My phone is 248-854-2034. And the website, very creatively, is citizensclimatelobby.org. Thank you.
And that's if you're interested in joining the Citizens Climate Lobby. And thank you everybody for watching and for coming.